Okay, so we're going to look at a more detailed example about doing max power transfer. So remember, on the previous lesson we learned that max power transfer occurs when the load impedance is equal to the conjugate of the Thevenin. So we're going to look at this circuit here, and we've got a 20 volt at angle 0 voltage source, 5 ohm resistor, a J3 ohm inductor, minus J6 ohm capacitor, and a 20 ohm resistor. And then we're asked to find what the load should be for max average power transfer, and then find the max average power transfer. Alright, so we're going to go ahead and do that here. Now, there's several ways we could approach this problem. I mean, we could just find ZL first, but what I'm going to do actually here is I'm going to find the Thevenin equivalent. And the reason I'm going to find the Thevenin equivalent is in any of these max power transfer problems, I find that it's easier to find the Thevenin equivalent first, because then not only is it easy to figure out what ZL is, but then when we're wanting to find what the max average power transfer is, we have a very simple circuit to look at. In fact, it's the circuit we had in the previous video, or some small variation of that. Alright, so to do that, I've already labeled here two nodes, VA and VB, because of course to find the Thevenin equivalent I need to find the open circuit voltage, and we can see here that V open circuit is equal to VA. So I'm going to go ahead and write a node equation here at node A, and I'm going to move this up just a tiny bit. So at node A, what do we have here? Well, we've got a current going that direction and a current going that direction, so we'd have VA minus VB over J3 plus VA over minus J6 is equal to 0. And that's a very simple equation, so I'm just going to go ahead and, just like we normally do, clear out the fractions. So I have J6 is what I'll multiply through by here in this case. And then if I multiply through by J6, we'd wind up with 2 VA minus VB, be careful with your signs, minus VA equals 0. And so we'd have 2 VA minus 2 VB minus VA equals 0. And then we'd have VA minus 2 VB equals 0. Now, we could go ahead and set this up as a system of equations, because that would be my first equation, and then go ahead and find, do the matrix thing. But when I see an equation that's this simple, I'm like, well, maybe it makes sense just to kind of rewrite this, because again, what am I'm looking for VA. So if I solve for VB here, because I'm going to get another equation here, I'd get that VB is simply just 0.5 VA, or 1/2 VA. So I'm going to kind of keep that in the back of my pocket as well. So then of course I'll go back to the circuit here. So we need to now look at node B, and we need to look at the currents going left, right, down here. So if we do that, of course we would get VB, so node B here, we get VB minus 20 over 5 plus VB over 20 plus VB minus VA over J3, and that this is equal to 0. And I'm going to go ahead and multiply through by 60 here. So if I multiply through by 60, I'd wind up with 12 VB minus 20 plus 3 VB plus careful here. It'd actually be minus J 20, right? Because, yeah, 3, 20. VB minus VA. So I'm going to go ahead and simplify things here. So we'd have 12 VB plus 3 VB minus J20 VB plus J20 VA, and that should be equal to 240. And then now I'm just going to simply take this equation here, substitute it into here. Now this is where, if I combined like terms here, I could have my second equation and my second unknown. Actually, before I do the substitution, I'm going to clean it up a tiny bit here. J20 VA plus 15 minus J20 VB is equal to 240. And so again, this, if you wanted to solve a system of equations, that would be my second equation. 15 and you could then put these into a matrix and solve it, but we can see this VB very simple, and I will substitute it down into equation 2. And if I do that, I wind up with J20 VA plus 0.5 VA 15 minus J20 equals 240. And then just kind of combining some terms together here. If we do 15 times 0.5, we'd have 7.5, and then we'd have minus J10 plus J10, so plus J10 V times VA equals 240. And then if we do that computation, we get that VA is equal to 11.52 minus 15 well, I always write my J's here, minus J 15.36 volts. So that's my Vthevenin, which I'm going to go ahead and convert that to polar, because I'll probably want it in polar, or I might want it in polar, I should say. And if I convert it to polar, I get 19.2 at an angle of negative 53 degrees volts. Alright, so that's my, again, this is just to emphasize again, this is my Vthevenin. Now, I'm going to find my Zthevenin, which I'll redraw the circuit, and of course, because there's only independent power supplies, I can just turn that off, and so when I redraw my circuit here, I'm going to have it with the power supply turned off. And if I have it with the power supply turned off, this would be the circuit I'd wind up with. And so this would be minus J6, J3, 20, and 5. And clearly we have the 5 in parallel with the 20. So 5 in parallel with 20 would be 5 times 20 over 25, which would just be 4 ohms. So I'll just go ahead and modify this diagram here as we're going through. So now I did that parallel combination, I've got 4 ohms. So I can now see that these here are in series. and those are then end result in parallel with this. So I have, ultimately I have 4 plus J3 in parallel with negative J6. And I mean, you can use your calculator to compute this however you want to. Whoa. I'm going to pause here. My computer just went crazy. Okay, we're finally back. So there's probably some weird jumping in the video there because, well, my computer went crazy here when I was recording. So, again, what do we have here? We have the 4 plus J3 in parallel with the minus J6. And of course, you can compute that however you want to. I would just go ahead and do the 4 plus J3 times negative J6 over, it would then be 4 minus J3. And if we do that, we get 5.76 minus J1.68 ohms. And so, of course, what that means here, if we want to draw this here, is that my Thevenin equivalent would be, and I'll write this in my rectangular form, this was 11.52 minus J15.36 and then I have a 5.76 ohm resistor and then a minus J1.68 ohm capacitor. And so we know clearly here that the load, now we can answer part, well, I mean, we could have answered part A quicker, but this is going to help us answer part B quickly as well. So we know the answer to part A now is simply that I should set my load equal to my conjugate of my Thevenin. So my load should be 5.76 ohms plus J1.68 ohms. And so if I draw the load on here, it would be, of course, a resistor of 5.76 ohms and an inductor of 1.68 J1.68 ohms. And again, that's so we can cancel out that reactance. And so for part B, now, to get my average power, max average power, well, we can just compute S of the load, or actually what you can do is you can just do S of the 5.76 ohm resistor, because we know that this is going to be P for the load, where S of the J1.68 ohm would be Q of the load. Because remember, resistors give me the real power, the P, and then inductors and capacitors give me that imaginary or reactive power. Okay, so we can do it either way. We'll get the same answer, but remember when we did this in the previous video, all we ended up having is that, well, let me make sure I can see the circuit. We wound up, I just computed, I put a current in here and I just computed the current. And the current, I'm not even going to write the equation down for it as far as the loop, because it should be pretty easy for all of us to see. 11.52 minus J15.36 divided by, and I'll go ahead and write the whole thing out, but you should be able to simplify this a tiny bit. As opposed to having to write it all out. Because the whole point is these reactances here are canceling. So we wind up getting the voltage here just divided by that resistance. So if we do that, except I didn't do it correctly because I didn't put my parentheses in. So let me redo that. We get, well, and I'll go ahead and write this as fractions here. We get, because it works out to be a nice number, 2 minus j 8/3, and this would be amps. All right. Now, in order to compute complex power, we know that my complex power is, well, there's two possibilities. You know, we could have, if we're talking about impedances, magnitude of I effective squared times the impedance, or 1/2 the magnitude of I squared times my impedance. And there's other formulas, of course, but which one of these two do we use? Well, it matters what we were originally given. If we go all the way back to the beginning of the problem, we were given volts, and this is, since it didn't specify, this is non-RMS. So that means if we go down here, which one do we have to use? We have to use this one. All right, so then we go ahead and compute here. So, well, first I'll just compute the magnitude of I squared. Which gets you essentially 11.11. And that's because if you look at the magnitude of I, I'll just write it off to the side here, magnitude of I is equal to 3.33 repeating. So 11.11 for I. And so then what do I get here? Well, my S, because again I'm only going to do for the 5.6 ohm resistor, because then this would give me my average power for the load would be 1/2 11.11. Looks like it's a bunch of 11s. I don't know why I put that in absolute values there. 1/2 11.11 times 5.76. And if we do that, we wind up getting that this is essentially 32 watts. Okay, so then that's it. We're done. So again, what did we compute here? We computed the max average power transfer, and I'm just wanting to double check some computations here because something feels a little off to me, but I think we did everything right. So we have 11.52 Okay. There's something here that you probably already caught because something felt off to me, and it is off. This here, when I did this computation here, I did this wrong. What I did is I divided by 5.76 as opposed to adding those two together. So let's just fix this real quickly. So that would mean that wouldn't be 2. This would be 1. And this would be 4/3. Which, going through here, what that means here, if we do we'd wind up with the magnitude of I being, sorry, can't use my calculator right here, 1.66 repeating, which means this number is now 2.77 repeating. So 2.77 repeating. And what that does is that actually changes this number to 8. So sorry about that little computation error. You probably already caught it when you were doing your notes there. And again, what I did is, and this is where you have to be careful, is I only divided by 5.76 as opposed to adding the two together when I got my current. All right, but everything else we did here is the same.